talking about the type 1 and type 2 phase diagrams in the previous lectures. So we will come to type 3 and type 4 phase diagrams. So again, let us consider the type 2 phase diagrams. I have already introduced cooling curves, but as you can see here, for a type 2 phase diagram, if I have to determine a type 2 phase diagram, okay, if I have to determine a type 2 phase diagram, there are various experimental methods. One of the experimental methods is using cooling curves. Now, in cooling curves, what we do, we prepare a sample of different composition, right? Say, for example, in a binary alloy, it will be from pure A to pure B. You can take any composition. And then for each composition, we will basically use for each composition we'll basically use a furnace. We will heat it up unless it melts, and then we'll start cooling it. So it's called furnace cooling. So as we cool it, so we will basically see with a certain imposing a certain cooling rate, we get this temperature time curve. So if you look at these, so for example for 0 atomic percent of B, so this is all in atomic percent. Then 0 atomic percent B, that means P or A, you get a cooling curve. Which is given like this. So your liquid phase is cooling down until it comes to the freezing temperature, the melting temperature. Now at the freezing or melting temperature, as you can see, the furnace, so when it is cooling down, so furnace is giving off heat, right? The furnace is giving off heat and it is cooling down because the furnace, so it is basically furnace cooling that I am talking about. So the furnace was heated up until the sample has melted and it has been heated up to certain temperature. So at a given temperature, right? Say for example, this is a temperature at which it was heated up. Okay, TF. Okay, let's not TF. Let's call it TEXP. So this is like TEXP. So TEXP is the temperature at which, if you look at TEXP, so if you look at TXP, for example, is experiment a temperature at which the furnace was heated up for different compositions. Like these are all compositions expressed in terms of atomic percent. If it is 0 atomic percent, it is 0 atomic percent of B. That means 100 atomic percent of A. Now 100 atomic percent of A, what you are seeing is called a cooling curve. So basically, it is cooling down till the freezing or melting temperature of A. Once you are at the freezing or melting temperature of A, you basically see a horizontal line. Why? Because at the freezing temperature of A, from the liquid to solid transformation, during liquid to solid transformation, as we have already observed before, what you will get is with evolution of latent heat, right? Latent heat is given out, or heat of transformation is given out. Now this is given out and the furnace is cooled, right? So basically, so giving out the heat also raises the temperature. So if you think of it, as temperature is dropping within the furnace, and then because of this latent heat evolution, there is a temperature that goes up. So at that, so basically at the melting or freezing point where the latent heat is released, at the freezing or melting point where the latent heat is released, you can see that there is a temperature, there is a heat given up which increases the temperature of the furnace, and there is a, and also as you can see that the temperature of the furnace is going down. So these two opposing events interact, right? So basically they are the same. Now in such a case, what will you see? You will see that the temperature has now basically now, so you see it here. So the latent heat means the latent heat is giving, so as the latent heat is released, the temperature of the furnace is increased and the temperature of the furnace is slowly dropping. So as a result, what you see is such a curve here, right? And since it's pure A, there is no composition dependence. So you will not see a slope, but you will see exactly horizontal line here, right? This line segment, right? Indicating this horizontal line segment indicates the onset of freezing, right? The onset of means indicates the arrival of the freezing temperature or the transformation temperature. So this temperature is the transformation temperature for pure A, right? For pure A, this is the transformation temperature. This line gives me that this is where the transformation temperature or melting temperature or freezing temperature, whatever you call it, is. And then beyond that, so this cooling, now you tell why is this slope? The slope is coming because of the conductivity, right? The conductivity, how conducting the liquid is. So this is this blue curves, the blue segments are for the liquid, and the red segment is for the solid. Now, if you see, when we look at the blue curve or the red curve, the heat release is basically driven by the heat release, the rate of release of the slope is basically dependent. The slope is basically dt. The slope is basically dependent on the conductivity of the liquid and the conductivity of the solid. And the conductivity of the solid, because as you know, actually it depends on alpha, and which is basically K. K is the conductivity, pi rho Cp. Cp is the heat capacity, and K is the conductivity, and rho is density, and so it is proportional to K by or it is equal to. Sometimes this itself can be a function of position, but if you do not assume this to be a function of position, you can write dt equals to Kr del T. Is K by rho Cp, and this can be like del to T del x square. If I look at this as a 1D problem, but it may not be a 1D problem, it can be a full-blown 3D dimensional problem. This is a heat transfer equation. So what I am trying to say, that ultimately it depends on the thermal conductivity of the liquid. So the slope of these blue curves, or the red lines, or the blue lines for different compositions depend on the thermal conductivity of the liquid, the thermal conductivity of the solid, the heat capacity of the liquid, heat capacity of the solid, and also the density of the liquid and density of the solid, which can differ, right? The slopes need not be same, right? So because it can be different for the liquid and the solid. Also, it will vary as a function of composition. So all are possible. So as a result, you will get representative cooling curves, and this is for different compositions. So this is so in our case, this is like the composition 0 atomic percent, and then at 0 atomic percent you get a horizontal line, and this horizontal line represents the freezing or melting temperature, right? This is where the latent is given up, right? Latent is evolving. The latent is evolving, which raises the temperature. The raising of the temperature is compensated by the cooling down of the temperature, right? The falling of the temperature, raising and falling are competing, and so there is this horizontal line which represents this evolution, and beyond that, again, just below that, you start continuing the cooling process, right? You start continuing the cooling process to some specific temperature. Say, for example, when the furnace temperature is similar to the ambient temperature, right? So that is where we stop the experiment. Okay. So similarly, I can start with, so this basically, if you now draw a horizontal line and extend this horizontal line, you will basically, here what you hit is the melting point of puree. Okay. Now you go to the 10 atomic percent. In 10 atomic percent, the idea of the liquid cooling remains the same, right? The liquid cooling remains nearly the same. In fact, here it looks almost parallel. However, it will not be parallel, right? The conductivity of this 10 atomic percent means this liquid containing 10 atomic percent of B can be different from that with 0 atomic percent of B, right? For puree. So with 10 atomic percent of B, what you see is, although it seems parallel, but it will not be parallel. So this is something that I am just trying to say. Now you have this. Now you see, and then you have this, right? This is the cooling segment. This depends on the conductivity of liquid. This segment depends on the conductivity of solid, right? However, if you look at the green segment, the intermediate segment, what you basically see, this intermediate segment, the sloping intermediate segment, is nothing but the segment where you have liquid plus solid coexistence. You have two-phase coexistence in the segment because of the change in slope. So this is one slope. Now there is a change in slope, and then it comes back. Now this change in slope, why is this not horizontal? This is not horizontal because I would like to say that it is not horizontal because if you take one composition which is given by this yellow line, if you take one composition given by the yellow line, you see, you start your freezing here, right? You are going down the yellow line. So you're going down, down, down. And then once you are, say, for example, this is 10% A, 10 atomic percent A, or 20 atomic percent A. Now, in 20 atomic percent is, again, if you look at 20 atomic percent, you have these curve, and then you have this slopey region, right? The slope changes, and then again the slope changes when it's solid, right? So you have this region which represents liquid plus solid. Now, how is that happening? Why is it sloping? Why is there a slope here? Why is it not horizontal like pure A? Why is this line, why is this line not as horizontal as here? This is because in these cooling, there is a continuous composition change. So when you are looking at 20 atomic percent of B, 20 atom solution containing 20 atomic percent B, you never get a horizontal line here, but this liquid plus solid coexistence, right? Here also this represents liquid solid coexistence. This is also liquid solid coexistence, or this is also liquid solid coexistence. However, this liquid solid coexistence is continuously sloping, right? It is sloping, it has a slope. This liquid solid coexistence has a slope. This liquid solid coexistence has a slope. So why is that slope there? So you go there, for example, this liquid is cooling down, cooling down. Now at this point, you basically start getting, so this is your solidus line, right? This is your solidus line. And now at this point, as soon as you just go at the hit the liquidus, you start seeing there is a solid of composition given by this point, which you start nucleating, right? Which will nucleate in the microstructure. The microstructure initially consists of entirely liquid. Now, at this point, you start getting nuclei of the solid phase, Now you go further just below. Now if you go below, you start to see that the liquid phase and the solid phase composition has changed, right? The liquid now has more of A, right? Here the liquid initially had only 20% A, but now the liquid has more of A, right? So basically the liquid will have slightly more A. Now you go further down. If you go further down, you will suddenly see that the liquid composition and the solid composition are changing further. Solid has more A, the liquid has more A, the amount of B overall is getting distributed, and you have a different composition of the solid and the liquid, right? The solid and liquid composition continuously changes until it goes to the solidus, where you have solidus and the remaining liquid. So if you now go to the solidus point, when you are touching solid, so basically remember, this is what I am trying to say, that this segment, the way you are thinking, may not be the case, because if you see, you have some solid here, you have some liquid here. Now this is your liquid composition. Now this is what is melting, and then basically this is what is freezing. So now if you look at that this is your liquid composition, now this liquid, when it is coming down, then again there is a shift in composition. So there is a continuous shift in the liquid composition that is getting solidified. Okay, when you have a solution, then basically there is a continuous shift in the composition of the liquid and that of the solid as solidification is progressing. As solidification is progressing, you will basically see a change in the composition of the liquid that is getting frozen and changing composition of the solid that is coming out. So as a result, your cooling curve will always show a slopy two-phase region, right? It will show us inclined two-phase region. So this inclination will be there. See here, all of these cases have inclination. Again, it becomes horizontal when you have pure B, 100% B. So on 100% B, you have horizontal line. Otherwise, you have this sloping lines, right? You have these different sloping lines. Now, if you look at the sloping lines and see, just follow my pointer. If you look at my pointer, and if you just see the change in slope here, and you can follow my pointer, you can change in slope here. So basically, you have got your phase diagram. So basically what I'm trying to say is this. So you have a phase diagram here. So if you look at that, drawing that here. Okay, basically what you have is the phase diagram, right? This represents the liquid solid coexistence. Then, so this represents the liquid solid coexistence level class S, and then there is S, and this is L. And see, this is what exactly I have drawn here, right? Temperature versus composition curve. So this is the temperature axis. This is the composition axis now, right? This is not time axis, right? Here it is time axis. In the cooling curve, this is the time and this is temperature, and these are the compositions, right? For discrete compositions, we have, for different compositions, we have different cooling curves, right? Now, I have looked at this two-phase coexistence region to draw this phase. So, and we have looked at this change in slope here. So, basically joined here, where we see this change in slope from liquid to liquid plus solid. And again, you have this liquid plus solid to solid. So, these points. So, all these basically mark the phase boundary, the liquidus boundary. So, this is the liquidus boundary, and that guy gives you the solidus boundary, right? So, basically, you basically see that how you obtain the, so this is your pure A and pure B. So, how you obtain the phase diagram, right? So, basically, your phase diagram it's like this way. So this one is like that, and this, yeah. So if you exactly do this, you will basically see a phase diagram like this, right? So this is your phase diagram that you have drawn, and this is again I have redrawn the phase diagram, the same phase diagram of type 2, right? So this is one of the ways of determination of phase diagram by doing this experiment of cooling curves. So basically, if you look at lead tin technique, there also you use these cooling curves for different types of phase diagrams. You use different types of the idea of constructing the phase diagram remains the same. You take samples of different compositions of A and B, then put it in the furnace, take it to a temperature where all of these will melt to liquid, right? Where all of these will melt to liquid. That means you go above the melting point of B, right? You have to go above the melting point of B, right? So this is what is your starting temperature. Your starting temperature should be above the melting point of B, right? Slightly above the melting point of B, where everything is homogeneously liquid. All compositions are homogeneously liquid. Now, for each of these liquid samples, you start doing this experiment of cooling, right? The furnace cooling. As cooling is happening, the liquid is cooling down. As liquid is cooling down, at one point it reaches the, at one point when it starts freezing, there you have this melting point or freezing point where there is a liquid solid coexistence. However, as you know, liquid solid coexistence for pure A will be at a different temperature than that of pure A and than that of a mixture of A and B. And depending on the amount of A and amount of B, as you can see, there will be a variation in the liquid and solid composition in the two-phase region as it cools down. As a result, as you know, that for any solution of A and B, there will be a change in slope, but this change in slope that you see here, this is basically marking the two-phase coexistence in a solution. Two-phase coexistence in a solution where there is a slope here, right? You can assume liquid and solid to be ideal solutions, and you can basically also construct this phase diagram analytically, and you can see that the idea remains almost there you basically are looking at a composition, and then you're trying to construct a tie line, right? You are basically trying to construct a tie line, and then do it analytically, right? You are constructing the tie line and then joining the ends. So but here, just because of this change in slope that is happening between purely the liquid phase and the solid phase, this change in slope, this intermediate change in slope, is basically marking the two-phase coexistence. Now, remember, for pure A or pure B, the two-phase coexistence is marked by a horizontal line, while for a solution of A and B, it is always marked by a inclined line, right? So this is how a cooling curve can be used to construct a phase diagram of type 2. Okay, for now, you see there is another method which is called X-ray diffraction. X-ray diffraction depends on the measurement of. Now it becomes easier to use X-ray diffraction, not in the case of liquid to solid transformation, but in the case of solid to solid transformations. Say for example, you have an alpha phase and you have a beta phase, and you have a separating alpha plus beta. Now in X-ray diffraction, basically we look at these different solutions and measure the lattice parameter. Now there is something called Weger's law. Weger's law basically states that the change in lattice parameter with composition, right? A of C, basically A of C is basically you can write. So as the composition changes, there is a change. There is a composition of the solution changes. That is, say for example, look at this condition. When you have alpha phase, as you go from pure A, as say for example at temperature T1, you go from pure A to the saturation value. The saturation value is the maximum solubility of B in A, right? Alpha is a solution or solid solution of B in A, right? Amount of B in A. This is the maximum amount of B that can dissolve in A at temperature T1. The maximum amount of B that can dissolve in A at temperature T1. Now, as you can see, continuously there is a change in the content of B. As B atoms are being introduced into A, okay, in the alpha solution, what you basically see, the outcome is basically a composition dependence of the lattice parameter, right? A composition dependence of the lattice parameter. So this composition dependence is given by something called Weger's law, which states A minus A 0 equals to, and Weger's law basically tells that the composition dependence AC, the A as a function of C, is a linear function. That means you can write A minus A naught equals to K times C minus C naught, where K is basically called the Weger's law constant, which is 1 by A dA dC. Okay, so basically what you are telling is A naught was your initial lattice parameter. Say basically it is based on the pure A, and now it is changing from A naught, and the change is basically proportional to how the change happens from C naught. Now C naught or A naught can be any arbitrary composition, means arbitrary composition and a reference lattice parameter corresponding to that arbitrary composition. Now as you can see here, that it's a linear relation, and this Weger's law coefficient is 1 by A dA dC, right? 1 by A dA dC, which is basically K, right? Now the idea is that if you know this K for different solutions, say for example for alpha, then you basically can plot the lattice parameter, and again the variation lattice parameter will be linear, right? The variation lattice parameter will be linear. So if, say for example A had small lattice parameter, now adding B, you increase the lattice parameter, it goes on increasing till it hits the saturation limit, right? Till it hits this limit. So this limit is where you get one lattice parameter, but now as soon as your composition enters the two-phase region, the lattice parameter does not change. It becomes horizontal. That there is no lattice parameter variation because you have now two phases, right? If you look at the other way, say from beta, so again beta, let us assume that pure B had more. Obviously, you can see from here that adding B increased lattice parameter. So pure B has the maximum lattice parameter. Now, if you go below pure B, that is, you have some A here, you have some very little amount of A here, a slightly more amount, up to this at this temperature. Again, I am doing at temperature T1, right? This curve corresponds to temperature T1. You have this saturation point. This saturation point is a maximum amount of A that can dissolve in beta, or beta is basically primarily B, right? So the maximum amount of A, so if you draw this vertical line, this is the composition. This is the maximum amount of A that can dissolve in beta. Now this A dissolving in beta, what does it do? It reduces or contracts lattice parameter, right? Pure B has the maximum lattice parameter. Now the more A is entering, the less is the lattice parameter, right? So the lattice parameter again shows a different slope here. If you look at this, there is a different slope here. However, within the two-phase region at temperature T1, there is no change in slope, and you see basically a horizontal line, right? Lattice parameter does not change. So basically, again, looking at this curve, you can see that this is at temperature T1, then you can have it at temperature T2, and so on. Say, for example, at temperature T2, the curve will basically look like something like, right? So basically, it will look something like this one. So basically, now you have this point and this point. So means, as you can see, again, you are getting these 2 points, right? These 2 points. So these 2 points correspond to these 2 points. Similarly, you can have, say, some points here which correspond to these 2 points at some other temperature. So as a result, again, you get the points at the phase boundary, join the points, and you get a phase boundary. You get a phase boundary that separates alpha from alpha plus beta, and this one separates beta from beta plus alpha plus beta. And remember that these phase boundary also represents a limit of solubility of one component in another. For example, this phase boundary, this alpha phase boundary, or sometimes it's also called alpha solvus, it presents the maximum amount of B that can enter A, or that can dissolve in alpha at a given temperature, right? As a function of temperature, because this is temperature axis, right? This is the temperature axis. So if you know that this is the temperature axis, so this basically gives you the maximum amount of B, right? Alpha, the solvus curve. The solvus curve gives you the solvus, which separates alpha from alpha plus beta, gives you, as a function of temperature, the maximum solubility of B in alpha, the maximum solubility of the solute B in alpha. Similarly, this curve represents the maximum solubility of A in beta. Beta is a B-rich solution, right? So basically, B is the solvent and A is the solute in beta. In alpha, it is an A-rich solution. So in alpha, A is the solvent and B is the solute. Okay, now we have done this. Now we'll go back to the phase diagram, type of phase diagram. So we have looked at phase diagrams of type 1, where there was infinite solubility of A and B in the liquid, right? Or basically, it was completely soluble. A and B were completely soluble or infinitely soluble, or in the liquid state. However, in the solid state, in type 1 phase diagram, you had zero solubility of A and B, right? A and B coexisted as pure A and pure B in the solid state. In the solid state, pure A and pure B do not mix. For example, bismuth, cadmium, they do not mix at all. However, in the liquid state, they completely mix, right? They completely mix. See, this one has a practical example. This lens, one practical example is an isomorphous diagram between copper and nickel. Similarly, the type 1 phase diagram also had a practical example, and the type 1 phase diagram, the practical example was bismuth, cadmium, right? This also has many practical examples. So this is a case in type 3. You have a case where, although so type 1, you had infinite solubility of A and B, or solubility of A and B in the liquid is infinite, but solubility of A and B in the solid was 0. Now type 2, what happens? Solubility of A and B, or A and B in the liquid is infinite, as well as in the solid, that is infinite. So basically, it is completely miscible or completely soluble. A is completely soluble in B, or B is completely soluble in A over the entire composition range, right, in the liquid state as well as in the solid state. That gave rise to lens-shaped phase diagram. However, type 3 is a very special case of type 1, and it's a more general, in fact, I'll tell you that it's a more general case of case 1, and this in type 3, what we are looking at is the solubility of A and B in the liquid is infinite. However, the solubility of A and B in the solid is limited or finite, right? It is basically limited. The solubility is limited. There is a solubility limit. So when I tell solubility is limited, that means in the A solid, the limit of the amount of B that can dissolve is limited, right? That is a limitation on solubility, or there is a solubility limit, right? At a given temperature, there is a solubility limit. So for example, this curve, the solver's curve, as I discussed before, represents the solubility limit of B in alpha solid solution as a function of temperature. So this is the maximum, this is called the solubility limit, right? Because this is the maximum solubility of B in alpha. Alpha is a rich solid solution as a function of temperature, right? As a function of temperature. Now, as you can see, that means even for beta, there is a solubility limit, right? There is a solubility limit. This represents the limited, the maximum solubility of A, okay, the maximum solubility of A as a function of, so for these, say, for example, I draw a temperature line like this, a horizontal temperature line like this. So you can see that it marks my point here. So this basically is the maximum solubility of A at this given temperature in beta or B rich solid solution, right? Okay. And remember, alpha and beta can have different crystal structures, right? Alpha and beta can have different crystal structures, and that's why alpha and beta are separated here. And instead of A and pure A and pure B, we are now having these solver's curves, right? These solver's curves, right? You have these solver's curves, and you have this alpha single phase region, beta single phase region, and this alpha region, the maximum solubility, basically you will see the solubility limit of B in A the B in alpha increases with increasing temperature, right? It is increasing with increasing temperature, because see, here it was the solubility limit, and then this point was the solubility limit. Then as you go to higher temperatures, the solubility limit of B, so this is the amount of B in the saturated alpha solution. So in the saturated alpha solution at this temperature, this is the amount of B, right? So the amount of B that is dissolved in alpha goes up as the temperature goes up, right? So this is basically the solver's curve represents. Now in the beta solid solution also the same thing. The amount of A that can dissolve in beta goes up as the temperature increases. Now look at a very special point here, which I have already discussed this type of a reaction. So the reaction previously we considered is basically liquid goes to A plus B, where pure A and pure B in the solid state, right? The liquid transforms to pure A and pure B. One thing you have to understand, and this is again, I am repeating myself. So the one thing you have to understand is the point E. At the point E, where there is the transformation from liquid to alpha plus beta, is a very special point. Why it is special? From Gibbs phase rule, you can understand you have two components, three phases coexisting, and you have the degree of freedom equal to 0, right? So basically, degree of freedom equal to 0 at this point. Even at this point, you have liquid alpha beta coexistence, or at this point, right? Along this line, at this point, what are the phases? So now you will tell me what is this composition. This is the liquid composition. This is the alpha composition, terminal composition, and this is the beta terminal composition. So at this temperature, which is the eutectic temperature. So at the eutectic temperature and composition, this is called eutectic composition. You will see something interesting. If you look at freezing, the liquid is now coming down along this white line. The liquid is now coming down, and at this point, you see exactly the same horizontal line, right, which does not depend on composition, right, and then it transforms into two phases, alpha and beta, right. So this is basically a eutectic transformation, and the eutectic can be in the form of lamellae, in the form of rods, right. It can appear in the form of alpha plus beta, arranged in the form of lamellae, alternating lamellae. They can be in the form of rods, they can be in the form of plates, right. So basically you have like alternating plates or lamellae. So all different types of eutectic microstructure can be obtained, but you have to look at the eutectic reaction. The reaction is very interesting because, first of all, this E represents a freezing point or melting point of the mixture of A and B at the eutectic composition, or mixture of two phases, alpha and beta. This eutectic point represents the lowest melting, right? This is the lowest melting point of the solid. So the solid, if the solid consists of, say, some amount of alpha, so if the solid is having this composition, then this solid below the eutectic temperature is having only alpha plus beta, right, below the eutectic temperature. So this composition below the eutectic temperature will have alpha plus beta. Now at this temperature it just transforms to, it just has a transformation to liquid, and so you just go slightly above, you have the liquid of same composition, right? When it comes down to alpha and beta, then you definitely at a given temperature you have alpha of this composition and beta of this composition, right, at an equilibrium. So basically this is a eutectic represents a low melting mixture of phases, right? A low melting mixture of phases. Okay, our eutectic composition is a low melting composition, lower than that of pure A, right? That of pure A and pure B, right? So eutectic temperature is a temperature that is lower than either of the melting points of A and B. This is for a binary system, and this is the invariant reaction. Al transforms to alpha plus beta, or alpha plus beta transforms to, right? This is the invariant point E below the melting point. So it is basically below the melting points of pure A and pure B, right? So this basically is a very useful, this is a very useful concept in casting, right? So basically if you look at casting, you don't want to go to temperatures like that is like very high, like if you're looking at casting of refractory alloys, you don't want to go to you do not really want to go to temperatures which are like that corresponding to like the pure A or pure B melting point, right? But you can now go to temperatures, say for example, you can now go to temperatures like this eutectic temperature that is there, okay, which is lower than either of the melting temperatures, and at this temperature you can do a casting, right? So if you do a casting, what will happen? The liquid will solidify into, if the cast structure will contain a mixture of alpha and beta arranged in the form of lamellae or rods or whatsoever, right? So they can be they will be arranged in this different this microstructure typically that you obtain is called an eutectic microstructure, which is a mixture of these alpha and beta phases. And so basic, but what happens is, as you see, the liquid of these composition as shown by this red dot, the liquid of this composition will basically transform at a much lower temperature, or freeze at a much lower temperature, or solidify at a much lower temperature than either of pure A or pure B, and it will form a eutectic mixture of phases of alpha and beta. So eutectic mixture of phases alpha and beta. I don't want to go back or explain the lever rule and tie line. I just want to tell these are the salient points. We are representing this invariant reaction. So this is the invariant reaction. Now think of a point here. So if you see, I have marked with various phase regions. So within one, if I look at one, F equals to 2, right? Because this is 2 components minus 1 phase plus 1. So this becomes 2. Now at 2, F equals to 2 components minus 2 phases plus 1. So F equal to 1. So basically, when you have point 2, F equal to 1. Now at point 3, it's a special point, F equals to 2 minus 3 plus 1, right? Now 3 is the eutectic point, which basically gives you 0. So basically, the point E, you cannot independently specify. So basically at point E, degree of freedom 0, that is the composition and temperature, both have to be specified, right? Composition and temperature both have to be specified. There is no degree of freedom, right? You cannot basically specify temperature or specify composition, or you can specify both. Your temperature and composition, as soon as we are thinking of a eutectic point where 3 phases coexist, the composition and the temperature are already fixed, right? The composition and the temperature are already fixed. Now you can see here that this eutectic point, this is the point where you have the 3-phase coexistence, right? 3-phase coexistence means degree of freedom equal to 0. Now if you look at this point or this composition, right, at the eutectic temperature, you again see a liquid alpha beta coexistence, right? Liquid alpha beta coexistence. Now the idea that you have, then why is this E so different? Because when you are solidifying here, you see that this liquid of composition, this is the liquid composition. You see that this liquid upon entering the below the liquidus, it will transform to alpha of certain composition. Now, now there will be some alpha of certain composition. Now it go a little less, little more. Then you will have another liquid composition here, and this will be your solid composition. Now with this liquid composition, this liquid is now going to solidify. So as this liquid is solidifying, again you see the change in composition of the liquid. So as you can see, the liquid becomes more and more enriched in solute. That is, the solute is getting rejected to the liquid, right? And the alpha becomes more, so alpha again also becomes more and more. So basically the alpha composition is also changing, right? The alpha composition is also changing. Alpha is containing more B, but the liquid is also becoming enriched in the solute, right, on this side. In this case, say for example, if I take a composition like this, here you will have the first beta here, and now as you just go below, you will have the liquid composition changing and the beta composition changing, right? The beta is becoming basically the solid that you are forming is becoming slightly poorer in B, right? It is becoming more enriched in A, right? So again, if you look at beta from the point of view of beta, A is the solid and B is the solid, right? B is the solid. Now we look at a phase diagram. Now look at a problem here, the problem of phase equilibrium, right? At the temperature, say for example at temperature T1, right? You are looking at a temperature T1. This is the given by this horizontal line. This is your temperature T. Now at temperature T1, these are the saturation compositions. These are the equilibrium saturation compositions. Like this one, these. So this point and this point are the equilibrium compositions. So this basically represents at temperature T1 the alpha beta equilibrium, that is or alpha beta coexistence, and the compositions at which alpha beta and coexist are XB alpha sat and XB beta sat, right? XB beta sat or saturation or XB alpha saturation. So this is basically the saturation or the solubility limit at temperature T1, right? This is the solubility limit at temperature T1. And if you look at the style line here that we have drawn, this N composition is the alpha composition, and this guy is your alpha composition, and this is your beta composition, and this alpha composition and this beta composition coexist, right? Alpha and beta coexist. Now, if they are coexisting, that means the chemical potentials are equal, right? If we use B instead of A, we can use B or A. It does not really matter. You see mu B alpha equals to mu B beta, right? And this mu B alpha equals to mu B beta at XB alpha saturation and XB beta saturation, right? Because XB alpha saturation and XB beta saturation are the equilibrium values, right? We have got that in from the tie line. So XB alpha saturation is the equilibrium composition of the alpha phase, which is in equilibrium with the beta phase with equilibrium composition XB beta saturation, right? Now, and at these compositions, the chemical potentials of alpha and beta with respect to B means basically chemical potential of B in alpha equal to chemical potential of B in beta. Similarly, chemical potential of A in alpha should be equal to chemical potential of A in beta. Here we are only considering one component B. Why? Let us assume that at this temperature T1, alpha and beta are dilute solutions. Now, if we consider alpha and beta to be dilute solutions in saturated alpha, this is very, very important point that I am trying to say. In saturated alpha, so this point is what I am talking about. This composition is what I am talking about at temperature T1, and this is your saturation composition, and this is including this. Now, at this point, in saturated alpha, B is the solute phase, right? And A is the solvent phase that we have already told. So now we are also assuming it's a dilute solution. Now, dilute solution which obeys, so you can tell now, we can do a little bit more and tell that this is basically ideal dilute solution, where the ideal dilute solution where Henry's law is obeyed by solute and Raoult's law is obeyed by the solvent. Okay. Now, if you look at the saturated alpha composition, you have B solute, B as solute, and A as solvent. In such a case, the chemical potential of B in alpha can be written as mu B0, which is the chemical potential of pure B, right? Chemical potential of pure B, or molar free energy of pure B, and then you have RT ln AA, right? But RT ln AB, say for example, alpha in alpha. RT ln A is the activity, or you can write this as RT ln XB alpha plus RT ln gamma B0. Gamma B0 is the Henry's law coefficient. Okay, so Henry's law coefficient, and you have RT ln XB alpha saturation, right? This is the XB alpha saturation is the composition. So you have mu B0 plus RT ln XB alpha saturation plus RT ln gamma B0. That is Henry's law. Now, but in saturated beta, you will see that mu B beta. Okay, because again we are assuming ideal solution. So B is solvent now. Now if B is solvent, B obeys. So here B obeys Henry's law. Right? In the saturated alpha, B obeys Henry's law. The solute obeys Henry's law. So because B is a solute. But in saturated beta, B is solvent. So basically here gamma B equal to 1 and AB equal to XB. So basically in such a case, mu B beta, right, because B is solvent, mu B 0 plus RT ln AB beta, which is basically AB beta is nothing but XB beta, right, saturation. So XB beta saturation is nothing but your AB beta when you consider Raoult's law, right. So you basically have mu B 0, which corresponds to the chemical potential of B in the standard state or the pure state of B. Okay, so this mu B 0 is nothing but the molar free energy of pure B, right. Now, if you look at this, if you compare this, you know that ultimately at this temperature, mu B alpha equals to mu B beta. Now, if you name this as equation number 1 and if you name this as equation number 2, you will have mu B beta equal to mu B alpha, right? So, you have mu B beta equals to mu B alpha, right? This one and this one are equal. So as a result, 1 and 2, the right hand sides are also equal. So if that is so, you have mu B 0 plus RT ln AB beta is RT ln XB beta. So if you see that mu B 0 is here, mu B 0 is here, so that cancels out, right? But you have now RT, and again you have another RT here. So this RT and RT basically they are non-zero, so they can be removed. So you have ln XB alpha saturation plus ln gamma B 0 equals to ln XB beta saturation, right? Because see, this is where B is solvent, so there is Raoult's law. It obeys Raoult's law. So basically from here you can find out what is gamma B 0, right? You have ln here, you have ln here, you have ln here. So basically, if you look at that, ln gamma B 0 is ln XB beta minus ln XB alpha saturation. So basically, gamma B 0 is basically ratio of XB beta saturation by XB alpha saturation, right? That basically gives you the Henry's law coefficient. This is something that becomes very useful. To understand, say for example, means if we have such a condition, if we already know the Henry's law coefficient. So basically now we can use this to find out the saturation, to find out the ratio at the saturation, and it becomes very useful to understand the phase diagram, right? It gives me a nice way to understand the phase diagram. So for example, I'll give you a problem. Nickel and an element A. There is an element A which is mixing with nickel, and they are related by a type 3 eutectic phase diagram. At 1000 Kelvin, A dissolves 4 atomic percent nickel and nickel dissolves 6 atomic percent A, right? A dissolves 4 atomic percent nickel. That means the A-rich solution has a solubility limit of 4 atomic percent nickel, and nickel-rich solution has a solubility limit of 6 atomic percent A, right? So nickel can dissolve up to 6 atomic percent A at 1000 Kelvin, and A can dissolve 4 atomic percent of nickel at 1000 Kelvin. So when I'm looking at A-rich solution, A dissolving 4 atomic percent nickel, then basically 4 atomic percent is the saturated solution, is the saturated composition of nickel in the A-rich solution. So nickel is here acting as a solid, right? Nickel here is acting as a solid. This is acting as a solute in the arid solution. And when I am looking at nickel dissolves, when I am telling nickel dissolves, the nickel is a solvent and it is dissolving how much? What is the limit? It is dissolving maximum of 6 atomic percent of A at 1000 Kelvin. Now what we are telling is calculate the oxygen partial pressure at which nickel dissolves, nickel dissolved in A to the extent of 1 atomic percent. So amount of dissolution is only up to 1 atomic percent, and then nickel dissolved is beginning to oxidize to nickel oxide. Okay, and we are also telling that A is more stable. A is more stable, right? Because either in the other case, A is more stable and it does not oxidize. Okay, so basically the amount of nickel that dissolves in A starts oxidizing. Okay, and if it is so basically if it has to start oxidizing, what should be the oxygen partial pressure is what we have to find out, right? So now we will go to certain. We will just take a little bit of aside, and this aside is nothing but the reactions, right? Thermodynamics of reactions. So we are looking at thermodynamics of. So we'll just visit a little bit of thermodynamics of reactions to solve the problem. We require a little knowledge of the thermodynamics of reactions. Now, as we know, delta G. So this is something that is well known. This relation delta G equals delta H minus T delta S, and we are considering this reaction where A is the small a moles of A solid react with small b moles of B solid to give small c moles of C solid and small d moles of D solid, right? So this lowercase d, lowercase c, lowercase d and lowercase a basically represents the stoichiometry or the balance, right? There is a balance of the amount, right? So amount of A is A moles, small a moles and or lowercase a moles, and amount of B solid is lowercase b moles. They react to form C moles of C solid, right? C moles of C solid and D moles of D solid. Now, in this case, what is the delta Z0? How do you find out? Now, see, each component is in equilibrium with its own vapor phase. That we already know. Each solid is in equilibrium with its own vapor phase. So, basically, we can tell AA in the gaseous phase or the vapor phase with a partial pressure of PA naught, right? Partial pressure of PA naught. That is the PA naught is the vapor pressure of the gaseous phase that is in equilibrium with the solid phase. So AA. So this is a reaction that we are talking about, a reversible reaction. AAG. G is the vapor phase. G means gaseous or vapor phase with a vapor pressure of PA naught, which is equal to AA solid, right? So because the solid and the vapor are in equilibrium. Similarly, we can write for G is basically gaseous state or vapor state, and PB naught equals BB solid. Similarly for C as well as for D, right? PC naught and PD naught. Now the PC naught, PD naught, PA naught and PB naught are the pressures when we are considering only pure A, pure B, pure C or pure D, right? That is the vapor pressure. So PA naught, for example, is the vapor pressure at equilibrium between the solid A, pure solid A and vapor of A, right? Vapor of A and pure solid A, the equilibrium, basically at that equilibrium, the vapor pressure is PA naught. Similarly, PB naught is the vapor pressure when B solid is in equilibrium with the B vapor phase. Now, all these equations that I have written, all are equilibrium, right? These are all equilibrium equations. So basically, the delta G here will be equal to, so there is a delta G naught here to understand the feasibility of this reaction, right? Delta G naught is negative. Basically, if you look at delta G naught which is negative, then basically this reaction is possible. If it is equal to 0, then all of these are in equilibrium at that given temperature and pressure. And then if delta G0 is positive, then basically this reaction, the forward reaction AA plus BB equal to C plus DD at the temperature that we are considering may not happen. But what I am talking about, that each component in its pure state is in equilibrium with its own vapor phase, right? Each component in its pure state, right? Pure non-reacting state, right? This is a pure non-reacting state where we are looking at solid vapor equilibrium and the vapor pressure of PA naught. Similarly, there is a vapor pressure of PB naught. and then PC naught and PB. Now, if you look at that, if you add all of this together, so you have, say, a delta G1 or delta G2 in this case, because it's an equilibrium, delta G2 equal to 0, delta G3 0, 0, and G5 is 0. So basically, if you look at that, if you write this, so A solid, and here again there is an A solid, B solid, again B solid, and then you have C solid and D solid, and here also you have C solid, D solid. So basically, what we are now looking at is the reaction in the vapor phase. Now, if you look at that, this is like AA vapor at partial pressure of PN, at an oxygen pressure or a vapor pressure of PA naught is reacting with B moles of B, which is again in the vapor phase with the oxygen pressure of PB naught, and here also you have C mole and it produces C moles of component C in the vapor phase, right, in the vapor phase with the vapor pressure of PC naught, and this is PD naught. Now remember, naught basically is the superscript that we use for pure components. Remember, it's like pure A, pure B, pure C, and pure D. The vapor pressures, right, at equilibrium are the PA naught, PB naught, PC naught, and PD naught respectively. Now delta G6 then, basically if I sum, delta equal to delta G, right? Now at equilibrium, that is at equilibrium, and we are assuming, say, the ambient pressure is 1 atmosphere. At equilibrium, you basically change the subscript. So basically the superscript is now E, right? The superscript is now E, right? So basically what we are telling is at equilibrium, where the overall pressure is 1 atmosphere, you have this reaction where A moles of A in the vapor phase at an equilibrium partial pressure of. So here we are looking at an equilibrium partial pressure of component A, right? Equilibrium partial pressure of component A. This is equilibrium partial pressure of component B, and that of C and D. And this G indicates vapor phase, and they are combining. If they are combining with total pressure of 1 atmosphere, that this reaction delta G, the change in free energy for this reaction is equal to C, right? Because it's an equilibrium. Now, if it's an equilibrium, for example, here, so this is delta G2 equal to 0 because this is an equilibrium. This is again an equilibrium. This is again an equilibrium. Now we are having a slightly different equilibrium because of this E. E basically tells the equilibrium partial pressure when A and B are reacted together. So you have an AB mixture where it becomes the PAE is the partial pressure of A in the vapor phase at equilibrium, and at equilibrium with the entire mixture of A and B. Now see, basically total pressure is 1 atmosphere. Now as you can see, for each component I, there is a change in pressure from PI naught to PIE, right? From PI naught to PIE. Now if that is so, you know dG equals to VdP minus SdT, and you are telling T is constant, so dt equal to 0, right? dt equal to 0. So then dG equals to RT dlnp and delta GI. So basically, if I integrate for each component, delta GI equals to RT ln PI equilibrium by PI naught. PI naught is the pressure, the vapor pressure of component I in the pure state, when the component I is in the pure state, and this is vapor pressure of component I when that is in the equilibrium state with other components, right? Other reacting components, right? So PIE is the partial pressure of component I in the state where I is reacting with, means there is a reaction between these I's and they're all at equilibrium, right? So basically PIE is basically when A, B, C and D coexist, right? They coexist. Now if you look at that, you had this reaction, right? A moles of A in the vapor phase with PA naught as the pressure, the vapor pressure, and B moles of B at a vapor pressure of PB naught, okay, in the vapor phase, they react to form these C moles of C and D moles of D, where again these are also vapors with the pure, the standard pressure being the standard vapor pressure of PC naught and PD naught. These PD naught and PC naught or PB naught and PN naught, they correspond to the vapor pressures at equilibrium of pure solid with with its own vapor, right? Pure solid with its own vapor, right? However, what we have to look at is that there is a, so when A, B, C and D coexist, then there is this, that A and B are reacting to form C and D. So if you look at that, A and B, when they react, the pressure has no longer remained PA naught or PB naught, because you are now reacting them together, you are mixing them together. So as a result, you will see the partial pressure becomes PA equilibrium and PB equilibrium, so that the total pressure remains 1 atmosphere. And you have A moles of A equals to A moles of A, but you have now PA equilibrium and you initially had PA naught, right? The equilibrium pressure is PA equilibrium. Equilibrium partial vapor pressure is PA equilibrium. Similarly, PB equilibrium is the equilibrium partial pressure of component B. Now again, the B moles are getting transferred, so they are getting transferred from here to here, so which is equal to BB. So this is a pure state, and this is where there are reaction. So basically, you have PBE, and here you have PB naught. Similarly, for C, now in C, you had this pure state that was known. Now this is now converted to G. This is the vapor phase, but PC, that is in equilibrium, right? This is the equilibrium vapor pressure, right? The equilibrium vapor pressure when both of them coexist. Now in that case, the delta G2 in this reaction, right, from A naught equals to A equilibrium, right? There is this reaction. So basically, your delta G2 becomes ART, right? Because see here, this is for basically, if you look at dg equal to vdp minus sdt, this is basically what I am trying to say is that this is for 1 mole of component I, right? For 1 mole of component I, you have RTL and PIE by PI naught. But here you have A, because there is this A. Now A is the number of moles of A. So A is the number of moles of A, right? So basically delta G2 is A, RT, ln PA equilibrium by PA naught. Similarly, delta G3 is B times, B is the number of moles of B, RT, ln PB equilibrium by PB naught. And similarly, delta G4 is C is the number of components. So remember, these were the reacting components, right? These reacting components, you are already in PA equilibrium and PB equilibrium vapor pressure. Now, PA equilibrium vapor pressure or PB equilibrium vapor pressure is that vapor pressure where A and B both coexist, right? A and B coexist and they combine to form a coexistence of C and D, right? So basically, if you look at that, C and D originally exists in the pure state. C and D originally exists in the pure state. From the pure state, we have to go to the equilibrium state. Now, if you look at that, in this case, what will be delta G4? This will be PCO by PC, and this is also going to be PDO. O is the 0, PD 0. That is the vapor pressure where D, pure D solid, is in equilibrium with its own vapor at a vapor pressure of PD naught, right? PD naught by, this will be PD. If that is so, you have all these reactions, you can just add them up. If you add them up, what you basically get is AA. Now, if you see here, you have equilibrium here, you have equilibrium here, and you have the opposite here. So you have equilibrium, and see, you have also here PA naught, PB naught, and here also you have PA naught, PB naught. So this will cancel. So you have these one, where the superscripts are equilibrium. Similarly, on the right hand side, you will have these numbers because these guys and these guys will cancel out, right? So as a result, what you basically see is that AA reacting with BB again in the vapor phase, but you have now partial pressure of A at equilibrium with the partial pressure of B at equilibrium, and you have partial pressure of C at equilibrium and partial pressure of D at equilibrium, so that total pressure is 1 atmosphere. Now, in this case, delta G7, this is the equilibrium reaction. Now, in this equilibrium reaction, you have, right, when you have equilibrium between the reactants and the products, basically the free energy is 0, right? Delta G7 equal to 0 for this reaction. Now if delta G7 equal to 0, now if you see delta G7 is the sum of all these reactions, right? This one plus this one plus this one plus this one, right? So basically if that is so, delta G7 which is equal to 0, right? Because they all are at equilibrium. Delta G7 is nothing but delta G6, right? Delta G6, which is delta G1 0. So delta G6 plus summation over I delta Gi, and delta Gi is given by this, like delta G2, G3, G4 and G5. So basically you have delta G1, delta C6 is nothing but delta G1 plus RTLN, PC equilibrium by PCO, PD equilibrium by PDO, right? So basically you have, so this is PCO by, so you have delta G one equals to minus RT ln K. So PC equilibrium by PCO. So yeah, so PC equilibrium by PCO. So this is also, this will be PBO by PB equilibrium, right? Yeah. Now if I have this, yeah, so you have to be very careful here. This is your equilibrium, the way we are using the convention. So here this will be PD equilibrium by PDO and PC equilibrium by PCO. However, this will be, yeah, this will be O by E and O, E. So if you add them, what you get? So if you add them, you have PAO by PAE, PBO by PBE. Now if that is so, this is nothing but PAE, inverse of the PAE and PAO, and PBE by PBO. So basically you have ln PAO by PAE, and you have ln PBO by PAE, which is PBE. So basically ln, this is something that I tell, PBO by PBE is nothing but ln minus ln right? This will be minus ln PBE by PBO. It's just an inverse, right? This is basically 1 by PBE by PBO. So ln 1 is 0. So ln 1 minus ln PBE by PBO. Similarly, you have ln PAO by PAE is nothing but minus ln PAE by PAO. So basically, if you now rearrange, you basically get this relation, right? You have in the numerator PCE by PCO and PDE by PDO, and in the denominator this PAE by PAO, and this is PBE by PBO, right? And there is an RTLN, right? And you have this is delta G6 is nothing but delta G1. So basically, as you can see here, now delta G1 or delta, whatever you call it, you can call it delta G1. So delta G7 is equal to 0. So delta G1 is basically, call this as delta G. So yeah, so this is delta G1 0, right? Delta G1 0, which is equal to minus RTLN K, where this guy, we call it, this entire thing, we call it an equilibrium, the equilibrium constant, okay, for this reacting gases or reacting vapors. So this entire term is called K, right? Equilibrium constant. So you have delta G1 naught equals to minus RTLN K, okay. And now if you define AC or the activity of C as PC equilibrium by PCO, where PCO is the vapor pressure in the pure state, for pure component C. PC equilibrium is the vapor pressure when you have a mixture of component A, component B, component C, and component D. So AI can be written as AI equals PI. I am just, instead of putting a E here, so it is nothing but PI EIE is that in the mixture, right? Is the partial pressure of component I in the mixture, or the equilibrium partial pressure of component I in the mixture. So basically, you can just write as PI by PI naught, right? Is the pure form. Not basically tells the pure form. Now, if you see dg is RT AI, right? So basically, we know the change in free energy is basically proportional to the change in activity, AI, right? AI and dg. Now, if I equate, so you have this S is the standard state, and if we just basically you are integrating this equation, so basically you get GI minus GI standard or GI reference equals to RT AI by AI naught, right? RT AI by AI naught. Now, if you look at this, nickel oxide is dissociating with half oxygen and nickel solid. Now, delta G naught for this reaction is 14,600 joules, which is basically nothing but equal to minus RT K. So, K comes out to be 2.34 into minus 8, which is basically activity of nickel. So, you have the products, right? And this is the reactant. So, this is the reactant, this is the products. So, you have ANI, right? Because it's a solid. And PO2 to the power half, right? There is a half here, right? So, half PO2, or basically you can write PO2 to the power half, right? So, this becomes PO2 to the power half. And you have ANI, the activity of divided by activity of nickel oxide, right? So, basically, you have the activity of nickel oxide. So, basically, if you look at that, see again, you have A here, right? So, the A goes here. So, basically, this is nothing but PA naught by PA equilibrium by to the power A. So, right, this is the stoichiometric coefficient. So, in this case, C, the small c is half, right? Half moles of O2, right? So, basically, if it is half moles of O2, then you have PO2 to the power half. So, you have PO2 to the power half and to ANI, right? These are your products in the numerator divided by ANIO, and that basically gives me the equilibrium constant. Now, ANIO is basically pure NIO is equal to 1. Again, ANI pure equal to 1. So, basically, if that is so, what will be the activity of nickel in 1 atomic percent solution? So, basically, you know, nickel rich solution where nickel follows Raoult's law because nickel is a solvent. A rich solution, nickel follows Henry's law. Now, X and I, basically, if you look at the nickel rich solution, the maximum solubility limit was 6 atomic percent. Look at the nickel rich solution. You had nickel dissolves, so nickel rich solution, the amount of A that dissolves is only 4 atomic percent. So, amount of A that is dissolving is 4 atomic percent. And the amount of nickel that dissolves is only 6 atomic percent. Now, if you look at that, when you have X and I, so basically when you have X and I equals 0.94, corresponds to A and I equals to 0.94, right? So basically, if you look at this, so the relation, so if you look at the relation, what is the relation that we obtained there? We obtained gamma B0, right? Where I am looking at is gamma B, XB beta by XB alpha, right? You have XB beta and you have XB alpha. So XB beta saturation is 0.94 nickel, right? 0.94. So XB beta, where nickel is basically a solid, XB beta, where basically nickel is a solution, right? Nickel is a solvent. So nickel, the amount of solvent is basically X and I comes out to be 0.94, right? What is the X and I? See, at A dissolves, so basically A dissolves 4 atomic percent nickel. But nickel dissolves 6 atomic percent A, right? Nickel dissolves 6 atomic percent A. So X and I in this case is 0.94, right? And here, so X and I is 0.94, and here X and I is 0.04. X and I is 0.04 in the area. So basically, let us look at this. So if you look at this, A rich solution, nickel is solid, and there XNI equal to 0.04, and nickel rich solution XA equals to 0.06, right? A is the solid, but nickel is the solvent, right? Nickel is the solvent. That follows Raoult's law. So in this solvent, you have XNI equals to 0.94, right? So XNI equal to 0.94 in the nickel rich solution. So XNI equal to 0.94 basically gives ANI is also 0.94 because it's a Raoult's law. Raoult's law tells activity equal to mole fraction. Now this phase, this nickel rich solution is in equilibrium with the A rich phase with XNI equal to 0.04, right? This phase is in equilibrium. This phase is in equilibrium with the A rich phase with XNI equal to 0.04, right? So basically this phase is in equilibrium with XNI equal to 0.04. So this is the A rich solution, and nickel follows Henry's law. Nickel follows Henry's law. So if right, when you have A rich solution, nickel is a solute, and that follows Henry's law. And here the equilibrium is XNI equal to 0.04. So ANI, which is gamma NI 0 into XNI. Now, if it is so, ANI basically is 0.94 in one case, ANI is 0.04 in the other case. So you have gamma NI 0, which is the Henry's law coefficient for the nickel solute. The Henry's law coefficient is 0.94 by 0.04, which comes out to be 23.5, right? Which comes out to be 23.5. So ANI for 1 atomic percent solution. So basically, if it is so, ANI is basically gamma NI 0 into XNI. Now ANI at 1 atomic percent solution is 0.01, right? 23.5 into 0.01, right? It is 1 atomic percent of nickel. So basically 0.01 into 23.5 gives you 0.235. ANI comes out to be 0.235. ANIO is basically 1. So basically now if you plug in, ANI is 0.235, PO2 to the power half, and then ANIO is pure NIO is 1. So then basically, and K is this value, right? This value comes from this delta G equals minus RT and K. So basically this is 1, this is 0.235, and this is PO2 to the power half. Then basically what you see, the partial pressure of oxygen at which nickel oxide will basically, at which nickel will form nickel oxide is 9.6 × 10 pascals, right, or Newton per meter square. Partial pressure of oxygen is 9.6 × 10 pascals, at which nickel will oxidize to nickel oxide. Now we have another type 4 phase diagram, type 3 phase diagram, where we have another type of an invariant reaction, and that is called a peritectic, right? This is called a peritectic reaction. So basically this is called a peritectic reaction. Again, you have, so here what happens is you have liquid plus alpha. You look at this point. If you look at this line, along this line, so you have alpha solid solution here, you have beta solid solution here, but you see here, you have liquid, and then the liquid freezes. So basically, if I look at the concentration corresponding to point P, say, for example, so what you are seeing is you have liquid which is changed to liquid plus alpha, right, at this point P, where at the point P, this is the liquid composition, C represents the liquid composition, A represents the alpha composition, and you see there is some point P which represents basically the beta composition. So basically, L plus alpha at point P, you can see there is an invariant reaction where L plus alpha changes to beta. L plus alpha changes to beta, right? So this is called a peritectic reaction. So basically, if you look at this, A capital P C basically gives you this line where A is representing the, so at the peritectic temperature, A represents the concentration of alpha phase, C represents the concentration of liquid, and P basically tells you that the onset of this peritectic reaction, where L and alpha with these compositions basically transform to beta with the composition given by P, right? We put the beta at the composition given by P, right? So this is what is called a peritectic reaction. So basically you have pure liquid. So you have pure liquid. Now you have, as you go down at the peritectic composition, you have this liquid plus alpha, right? These alpha are there and liquid is there. Now, as soon as you go to the just below the peritectic reaction temperature, you start seeing this L plus alpha spontaneously completely transforms to beta, right? L plus alpha completely transforms to beta. Now, if you say go from any other point other than P, so you go to like something like this, like where you have liquid plus beta. Now, in such case, what you will see, instead of this that I formed where L plus alpha has transformed to beta, we get some amount of liquid as well as beta. So we get a mixture. So basically, if you look at this composition, we have a mixture of liquid and beta, right? Liquid and beta. So this is the liquid phase, and these yellow particles that you can see are the beta phase, right? So this is the idea, okay, in a peritectic reaction. So how does this peritectic reaction happen? The peritectic reaction, when it happens, basically you have L plus alpha. As you can see, this is L, this is L liquid. So this is the liquid that you have, and then you have this solid alpha, and what is happening is L plus alpha goes to beta, right? So alpha forms a core, and you have this beta shell which is spreading, right? Beta liquid shell that is spreading, right? Beta solid cell, sorry, not liquid. So you have alpha core and then beta solid cell that is spreading. So L plus alpha goes to beta, right? And the beta is basically the beta shell continues to spread, right? Now, if you look at a cooling curve corresponding to this composition, you can see that in these, up to this composition, you have pure liquid. But as soon as you enter this one, this is like liquid plus alpha, right? As soon as you enter this segment, you have liquid plus alpha. Now, liquid plus alpha, again, the composition is varying, right? Right? Or liquid plus beta. If you are going here, so first is liquid plus alpha. So as soon as you enter here, you have liquid plus beta, and that is the liquid plus alpha. As soon as you enter here, you are going from this line, you are entering this region, which is L plus alpha. Now, in this L plus alpha region, again, if you see that there is this tie line, so this tie line basically represents that the compositions will continuously change, right? So L plus alpha, the stage 2 basically is a sloping line, another slope, right? From pure liquid, the slope has changed to liquid plus alpha. Now there is this stage 3, that is this point where you have L plus alpha going to beta. The stage 3 is the most important one because it represents this L plus alpha going to beta, right? Stage 3. Then comes stage, now just below stage 3, if I go, then you start now having this stage. So you now having this liquid beta mixture. So beta particles are there embedded in the liquid phase. Beta particles are forming embedded in the liquid phase. So that represents stage 4. L plus beta represents stage 4. Now from stage 4, you go further down, you have this segment where you have pure beta. Again, your slope has changed again because pure beta is different from L plus beta, right? The conductivity will be completely different. Now, if you go farther down, you basically see that again this beta composition has changed to alpha plus beta. So alpha plus beta has a different slope. So you have all these places where 3 is the most interesting one, where you have the peritectic reaction or invariant peritectic reaction happening. Okay, so I will in the next in lecture, I'll discuss how this types of phase diagrams can come up. Okay, we will look at the free energy composition diagrams also as a basis of the phase diagrams in the next lecture. Okay, thanks for your attention. So we have type 3. So we'll also discuss type 4 and type 5 and type 6 phase diagrams quickly, and then I'll go to this idea of this free energy composition diagrams, because we are looking at this different equilibrium. right? We have also looked at how Raoult's law and Henry's law can be used to basically find the activity, right, of the activity coefficient, or the Henry's law coefficient, right? If we are considering equilibrium between alpha phase and beta phase, and in alpha phase, one component behaves as the solvent, and the solvent follows Raoult's law. In the other component, and the same component behaves as a solute in a dilute solution and follows Henry's law, right? Where again we can use Henry's law and Raoult's law to look at various properties of the phase diagram, right, of the equilibrium, of the phase equilibrium. Okay, so thank you for your attention, and we will go to the next lecture.